In this animation, a ball bounces off the ground. With each bounce, the ball achieves a lower maximum height. The law of conservation of energy states that unless work is done on or by a system, its total energy remains the same. The fact that the ball continues to lose energy indicates that negative work is done on the ball. The work done on the ball during each bounce is exactly equal to its loss in mechanical energy. As the ball falls to the ground, it does a small amount of work as it pushes away air molecules. The ball loses much more energy during the collision. When it collides with the ground, the impact causes the ball to vibrate and produce a sound that fills the room. The ball does work to create the sound, and this causes it to lose some energy. When the ball hits the ground, it is deformed and then returns to its original shape. This process creates a lot of internal friction, which causes the ball to radiate heat. Finally, when the ball hits the ground, it causes the particles that make up the floor to vibrate. When you add up all these forms of work, the law of conservation of energy tells us that the total work done on and by the ball equals the change in mechanical energy of the ball. Let's apply the law of conservation of energy to two people having a baseball catch. The boy on the right does work to throw the ball, and the other boy does work when he catches the ball. If we calculate the work done by the thrower, it would be exactly equal to the kinetic energy gained by the baseball. When the baseball is caught, the work to catch it is exactly equal to the loss in kinetic energy of the baseball. The thrower does positive work because he increases the total energy of the ball, and the catcher does negative work because he decreases the total energy of the ball. The work done on or by a system equals the change in kinetic energy plus the change in potential energy plus the work against friction. The system in the law of conservation of energy simply refers to the object upon which we are focusing. Let's make the green box in this animation our system. Since the kinetic and potential energy of the green box is increasing, we know that work is being done on it. The increase in kinetic energy and potential energy of the green box is exactly equal to the work done on it by the yellow box. Since the yellow box does 600 joules of work, the green box increases its energy by a total of 600 joules. This is a simulation of a famous experiment performed by James Joule. Two weights are attached to a rope. As the weight falls, they turn a paddle that causes the water in a chamber to move. Joule placed the thermometer in the water, and as the water moved, the thermometer rose. Joule proposed that the increase in the water's heat energy was exactly equal to the work done by the falling weights. To get the work done by the falling weights, you would simply need to multiply their combined weight by the distance that they fell. Here is a game that you might have seen in an amusement park. A hammer hits the bottom and drives an object up towards a bell. The object increases in total energy because work is being done on it. The law of conservation of energy tells us that the total energy the object receives is exactly equal to the work done on it by the hammer. If the change in potential energy of the yellow box is 30 joules, how much work did the green box do on it? The law of conservation of energy tells us that when work is done on or by a system, the energy of that system changes by that amount. Since the yellow box increases its potential energy by 30 joules, this must mean that 30 joules of work was done on it. When work is done on or by a system, it causes a change in mechanical energy of the system. It causes an increase or decrease in the kinetic and/or potential energy of the system. The change in the total energy of the system is exactly equal to the work done on or by the system. This is the end of my presentation on the work-energy relationship